Okay, today we're going to go through the chapter 18, Thermal Property of Matter. So this chapter is mainly talking about some concepts. Even you see a lot of equations in this chapter, actually you're not required to completely understand how to derive those equations. um, you just need to know there's an equation for that. So there's not too many calculations in this chapter. When you see some very complicated equations, don't be scared. You're not required to derive it, or sometimes you're not even asked to use it. You just need to know there is an equation to describe some properties, some thermal properties of some gases or other matter. So in this lecture, we're mainly introducing some concepts. In this chapter, we'll learn several topics. So first, how to relate the, okay, first let me change my cursor to pen. So first of all, we're going to learn how to relate pressure, volume, and temperature of a gas, which is P, V, and T. The relationship between amount PVT in gas. This is number one topic. For the number two topic, we will learn how the pressure and temperature of a gas are related to kinetic energy of its molecules. And then we will learn how the heat capacities of a gas reveal whether its molecules are rotating or vibrating. And then we'll learn how the speeds of molecules are distributed in a gas. And in the end, we'll learn what determines whether a substance is in a gas, liquid, or solid states. Okay, now let's start. So here is a picture of a frying pan. So you see the frying pan is on fire, so the temperature should be really high in this region compared to other regions like here. Um, when the temperature is very high in this region, in this chapter we'll learn actually the molecules or the gas molecules in this region, they will move faster compared to the molecules in the other regions. In the cooler region, the molecules are moving slower, and in a hotter region, the molecules are moving faster. And we'll explain why in the later slides. Um, and how do the atoms of a gas determine its temperature and pressure? We'll learn some equations to explain this. And we will see how the microscopic property of matter determine its macroscopic properties in this topic or this chapter. Okay, so first of all, quantities such as pressure, volume, temperature, and the amount of the substance are state variables because they describe the state of the substance. The equation of states relates the state variables. So here we show the ideal gas equation. So the ideal gas equation is an equation of states for an ideal gas. The equation is PV equals to nRT. So as I said, you don't have to learn how to derive the equations in this chapter. So most of the time in this chapter, it just give you the equation, tell you what's the equation and what are the relationships between the variables in some equations. It didn't tell you how to derive it. Sometimes it didn't even um, showed how to use it. But at least you see the equations here, which reveals the relationships between PV and T. And how this equation is derived? Actually, it's not derived. It's tested or it's derived from the experiment. It's not a theoretical derived equation. It's based on experiments. So the ideal gas equation shows the relationships among P, V, and T. So P is the pressure, V is the gas volume, T is the temperature. There are two other variables. N is the number of moles of gas. R is a gas constant. So R is constant, N is the moles. So in this equation, we see, let's say, there are three variables, states variables, which is P, V, and T. Let's say for a certain amount of gas, N will be a constant, and R is always a constant. So these two values, they are constant. So the three variables are P, V, and T. So the relationship among P, V, and T is, for example, if T is a constant, if you keep T to be a constant, when you increase P, the V will be decreased. And let's say if V is a constant, when you increase P, the temperature will increase. When P is constant, will increase V, then T is increased. So that's the relationship that we can know from the equation. The molar gas M, or molecular weight, is the mass per mole. The total mass of n mole is m total equals to nm. So this is what you have learned in chemistry. So we don't describe this too much here. So here, as we said, if T is a constant, then P and V, they should be a constant. So if you increase P, you will decrease V. Let's say this figure. Now, let's talk about a certain temperature T1. If the temperature is T1 with a constant, and you try to increase the pressure, then the V will be decreased, the volume will be decreased. So the curve of the ideal gas at temperature T1 is shown here. And if you increase the temperature to T2, which is a higher temperature, still the ideal gas we have similar behavior when you, let's say, when you increase pressure, then the volume will be decreased. This is the curve of T1, T2, and if you have higher temperature of T3 and even higher temperature of T4, you have their curves to be like that. So the higher temperature you get, then the further distance is between your curve and the origin. See, this is the distance between the origin to the curve T1, and that's the distance between origin to the curve T2. So when the temperature is getting higher, then the curve is getting further from the origin. Okay, this is a PV diagram when T is the temperature. The ideal gas equation, PV equals to nRT, gives a good description of the air inside the inflated vehicle tire. Okay, where the temperature is about 3 atmospheres and the temperature is much too high for nitrogen or oxygen to liquefy. Okay, so if P is very high, which is 3 atmospheres, okay, and the temperature is very high, then it's difficult for nitrogen or oxygen to liquefy. And in the tire, Let's think about the pressure in winter and summer. In the tire, we know um, the the V of the gas in the tire is almost constant because the volume of the tire doesn't change too much. It's almost constant. When V is constant, then when T increases, P has to increase due to the equation. That's why in the summer you have a higher pressure. In the winter you have a lower pressure. If you have the same amount of gas in the tire, because the V doesn't change. If let's think about if the tire is made of some materials which is very flexible, when the temperature is higher, the volume changed, then the pressure won't change too much. However, it's not. In the real case, um, the tire is made of some kind of material that keeps the volume, so the volume doesn't change. So when temperature changes, the pressure will change according to your temperature change. And this equation gives you um, the description of those relationships between P and T. Okay, now let's talk about the van der Waals equation, which describes interactions between molecules. Here we use gas molecule as examples. So the model used for the ideal gas equation ignores the volume of molecules and the attractive forces between them. So here is ideal gas model, and here is a more realistic uh, model of gas. Let's see what's the difference between ideal gas and realistic gas. So in ideal gas, we think the molecules are infinitely small, which means it doesn't have volume. So each molecule, each gas molecule has zero volume. This is the number one condition. Number two, they exert forces on the walls of the containers. For example, when it hits the container, it exerts some force on the container. However, they um, they don't exert any force on each other. That's ideal gas. For a realistic model of gas, the gas molecule have volume, so it's not infinitely small. It has a size. Um, and then because the molecule has a size, then it reduces the volume in which they can move. So because the molecule has size or has volume, then in the same container, the free space is reduced. And they exert attractive force on each other. So for example, let's say this is molecule 1 and this is molecule 2. Even they're far away from each other, they're not contacting each other, but they attract each other. So the longer distance they have, the weaker attraction they have, attractive force they have. However, when they're getting closer, the attractive force is getting stronger. Due to the attractive force, it reduces the pressure. So you can imagine that when the molecules are attracting each other, then when they hit the wall, it's not as strong as without the molecule attractions. When there is no molecule attractions, the molecule can hit the wall strongly. But when they have interactions with each other, when the molecule is hitting the wall, it becomes weaker. So that's why it reduces the pressure. And the last one, they exert forces on the container's wall. This is the same thing uh, as in ideal gas. And the forces between those molecules is van der Waals force. And the van der Waals equation is shown here, which describes the relationships between V, T, and P. So that's more complicated than ideal gas equation. So here is the ideal gas equation, PV equals to a constant T. And then in a more realistic model, it's more complicated. But don't be scared, we're not going to use this equation to do anything. You just need to know there is an equation to describe a more realistic model compared to ideal gas equation. Okay, now let's see some more PV diagram. A PV diagram for a non-ideal gas shows isotherms for temperature above and below the critical temperature. Okay, so here there's a little jump between previous slides and this slide. It gives you the concept of critical temperature directly without explaining what is critical temperature. So if you're interested, please do a search of critical temperature on Google. You will find some website or some useful information for critical temperature, which helps you to better understand this lecture. Okay, so here, let's see. For ideal gas, we see the PV curve is something like that. However, in a real case, um, for real material, the PV curve is showing in this way. For example, when you have certain amount of, let's say, gas, and the T is a constant at T1, if you try to uh, increase the pressure, then the volume is getting lower. So it will go getting higher pressure and lower volume. And then when it reach some pressure or some volume, the gas um, becomes um, liquid, and it's getting more and more liquid. Now it's a mixture of gas and liquid. When you keep reduce the volume, the pressure doesn't change. However, after all of the molecules are converted from um, gas to liquid, then when you continue to reduce the volume, the pressure will keep going up. So in the green region, it's the mixture of liquid and vapor. So this is for T1. For a higher temperature, let's say T2, you have similar curve like that. So the curve between A and B, it's a liquid vapor phase equilibrium region, means you have some gas, you also have some liquid at this condition. Okay, so above the critical temperature, there's no liquid vapor phase transition, and below critical temperature, the material condenses to liquid as it is compressed. Okay, you might be confused by what is critical temperature. Please do a search and you will learn that. So, generally speaking, or in a short words, you see, when the temperature is getting higher and higher, at some moment, at some temperature, it gets the critical temperature. At this critical temperature, when you try to reduce the volume, um, it only have vapor or gas and liquid mixture states at very short um, condition, or at only at certain V and P. It's not like a region of V so that you have the mixture. But when uh, when you have the temperature to be critical temperature, you will have the mixture of gas and liquid at just um, a certain volume. It's not a range of volume. You see, when it's below the temperature, you have a range of volume from A to B, range of volume from even bigger than A to B. This is called critical temperature. When the temperature is too high, then no matter what's the pressure, even you try to reduce the volume or increase the temperature or increase the pressure a lot, the gas is always gas. They don't transfer into liquid. So that's the uh, critical temperature. When your temperature is above the critical temperature, then there's no liquid, no matter how much pressure you given uh, to your system. Okay, um, molecules and intermolecule forces. So here shows two molecules. When the two molecules are put into space and they have a distance, then they have some interactions. Any specific mechanical compound is made up of identical molecules. So see, this is one molecule and this is another identical molecule. In gases, the molecules move nearly independently. The force between molecule in a gas varies with the distance between molecules. Okay, so this is the distance between two molecules. When the two molecules are getting farther, very far, then they have attractive force. And when they are getting closer, the attracting force is getting stronger and stronger. But when they are too closer to each other, their force between each other will becomes repulsive. So it's a very complicated, um, let's say, function of force depending on the distance r. If we describe it in a curve, it will be shown here in red. So the red curve is force, and in axis it's uh, r. It's a distance between two molecules. And the blue curve is potential energy. Now, first of all, let's look at the red curve, which is the force versus the uh, distance. Now, this is the distance between two molecules. When they are very far, it's attractive force, but it's very weak. If you try to put them closer and closer, when the distance is getting shorter and shorter, the attractive force is getting stronger and stronger. So please note that in the force curve, in the red curve, negative means attractive, positive means repulsive. So you will see the attractive force is getting stronger and stronger and stronger. Here, it's the lowest position, means at this distance, they will have strongest binding force. And then when the distance is getting shorter, the force, the attractive force is getting weaker and weaker. When it's R0, um, the attractive force is 0. And when the distance is getting even closer, the force becomes repulsive significantly. So when you shorten the distance, it becomes more and more repulsive. So uh, that's the force between two molecules. Due to the force, you can also get a curve of potential energy. So the blue curve is potential energy. So the potential energy is negative when it's far away, then it's getting more and more negative. So at the position R0, it has the lowest energy position. And then when the distance is getting shorter, the potential is getting higher and higher and then becomes positive. As we know, um, for those two molecules or any other systems, um, other systems prefer to be at the lowest energy position. So for this system, which contains two molecules, they also prefer to be in the lowest energy position, which is in the position of R0, in the distance of R0. When the distance between two molecules is R0, they are they, they are having the lowest energy, and this distance is called equilibrium distance. That in that case, they have the lowest energy. However, we know when when there is a temperature, um, the molecule will not be at the lowest energy position. They will try to, let's say, moving left and right, which is um, moving away from the equilibrium position. The same thing for the other atom. The same thing for all the atoms or molecules. When there is a temperature, they are vibrating, they're rotating, which um, moves them away from their equilibrium states. So that's when temperature is not zero, then they're they're not in the lowest energy position. So here's a present representation of thought. So the thought is in such a pattern. You have chloride ions in green and sodium ions in orange. So that's the size of chloride. It's big, and the sodium ions is small. So for those very small spheres, it's not representing the size. It's just representing the position. So for this part of the figure, it's representing the position and the size. So for this part, it's just representing the position. So don't be confused. And here it's uh, here is a picture of some other material, which is silicon crystal. So if you use a scanning tuning microscope image to see the distribution or the position of silicon crystal, you will see it looks like that. And this is a very small area. It's 9 nanometers. And each bead is one silicon atom. So these atoms are arranged in a such pattern. Okay, so moles and Avogadro's number. So moles and Avogadro's number, you have learned it in basic chemistry. So in any basic chemistry textbook, you will learn these things clearly. So here we'll mention it just briefly and quickly. If you don't learn it in any chemistry or other courses, please um, do some search on Google. You will find a lot of resources to explain what is Avogadro's number. If you understand what is Avogadro's number, then you understand everything related to moles. 1 mole of substance uh, contains a certain number um, of molecules of this substance, and this number is defined as such number of atoms of carbon-12 weighs 12 grams. So this is why this is how people first define Avogadro's number, because um, people first get 12 grams of carbon-12, this element, and people define this 12 grams of carbon-12 contains a certain numbers of carbon atoms. This number is defined as Avogadro's number. So because um, this much of or this many of carbon-12 weighs 12 grams, then this much of oxygen, let's say 16, should weigh 16 grams. So this is Avogadro's number. And this number finally is determined to be a big number, which is here. And the molar mass is mass of 1 mole. So molar mass equals to the Avogadro's number times mass of molecule of substance. For example, for carbon-12, you can do a search of what is mass of mass of the molecule of the carbon-12. When it times the Avogadro's number, you will get the molar mass, which is 12 grams. And when moles consist of a single atom, the term atomic mass is often used instead of molar mass. Okay, now let's talk about the kinetic molecular model of ideal gas. We have already mentioned it in the picture shown here. But now let's summarize the features of ideal gas. The assumption of kinetic molecular models are a container contains a very large number of identical molecules. And then the molecules behave like point particles that are small compared to the size of the container and the average distance between molecules. And the molecules are in constant motion and undergo perfectly elastic collision. And the container walls are perfectly rigid and do not move. So that's the conditions or assumptions of kinetic molecular models. And based on those assumptions, we can derive a lot of conclusions. So first, collisions and gas pressure. So here shows a collision. This is one ideal gas or one gas molecule. It's moving towards the wall, and then after hitting the wall, it's moving back. The molecules exert force on the walls of the containers. This is the origin of the pressure that the gas exerts. So this shows just the one molecule. You can imagine in the real case, there are so many atoms moving and so many atoms are hitting the wall. So if you sum all of the hitting forces, you get a force from the gas to the wall, and then that's the origin of the pressure. In a typical collision, which is shown here, the velocity component parallel to the wall is unchanged. So you see, when it hits the wall, the velocity is in this way and then change to that way. This is the initial velocity, this is the final velocity. If you decompose the initial velocity into x direction and y direction, and also do the same thing for a final velocity, you decompose the final velocity in x direction and the y direction, you'll figure out the Vy doesn't change. From here, this is Vy, this is Vy final. So Vy initial, Vy final, it doesn't change. The only thing change is V x initial and V x final. So the magnitude doesn't change. However, the sign changed or the direction changed. At the beginning, it's moving to the left, and at the end, in the final state, it's moving to the right. So it says the velocity component parallel to the wall doesn't change, which is y direction in this case. And the component perpendicular to the wall reverses direction, but does not change in magnitude, which is in x direction. First it's to the left, and then it's pointing to the right. Okay, if a molecule is going to collide with a given wall area A, shown here, during a small time interval dt, it must be within a distance Vx dt from the wall. If it's too far away, then it cannot hit the wall in a time interval dt. So it should be less than this distance. So the number of molecules that collide with the area A, shown here, during time dt is equal to the number of molecules within the cylinders that have their x velocity aimed towards the wall. So the cylinder is shown here, and the volume of the cylinder is A Vx dt, because A is the area and Vx dt is the length, so that's the volume. So in this volume, all the molecules which have x velocity towards the wall will hit the wall. Okay, now this is the equation part. We have a lot of equations without giving the way to derive it. You just need to know there's an equation. Sometimes you can use it to solve some problems. But the deriving of the equations are too complicated. We're not going to show it here. So total random kinetic energy, KTR, which means translational motion of all the molecules in a gas, is directly proportional to the absolute temperature. So KTR equals to 3 over 2 N RT. So N is number of mole of gas. R is constant, T is temperature. So when T is getting higher, your average translational kinetic energy is getting higher. So this means average translational kinetic energy per molecule depends only on the temperature. See, there's only temperature. There's no P or pressure, not on pressure, volume, or other kind of molecule. And here is another equation. 1/2 mv squared. What's that? Do you remember? We have learned it in energy. It's K, or kinetic energy. So that's the kinetic energy of each molecule. It equals to 3 over 2 or 3/2 kT. K is Boltzmann equation and T is the absolute temperature of gas. And the root mean square speed of the molecule in a gas is, so root mean square of root mean square speed of the molecule equals to first v squared and then square root, and then it equals to 3 kt over m, and then square root. This is from the previous equation. From the previous equation, you can get this equation. And finally, v equals to this number. Okay, to compute the root mean square speed, you can use this equation. So we model molecules as rigid sphere of radius r as shown in the right. So here, this is a sphere, and each sphere means one molecule. The mean free path of a molecule is the average distance it travels between collisions. For example, this one is traveled to the right. The average time between collision is the mean free time. In a time dt, a molecule with radius r will collide with any other molecules within a cylindrical volume of radius 2r and length vt. Okay, because this molecule is moving to the right in the velocity of v, so in delta t time, it will move v delta t in distance. So you can draw a cylinder, which is 2r, which is a circle with a radius of 2r, and then the length is vt. So any, let's say, sphere in this cylinder will be, actually I draw it too small, it should be bigger. So any molecule which is inside um, the cylinder will be hit by this molecule. The average distance traveled between collision is called the mean free path. And in this model, the mean free path is lambda. It equals to Vt mean, and it equals to V over 4 pi square root of 2 r squared n. So how did you get this equation? It's very complicated. So we don't describe or derive the equation. You just need to know there is such an equation. And then there are two more other equations. One the equation is that we don't derive it. It's just showing that we have such equation. So please read it by yourself. And here are some theory and experimental comparison. We don't derive the equation, and you just accept the concept, I guess, without any derivations. So just read those slides and try to understand it. Okay, so again, here is a comparison between theory and experiments. We're not going to describe it too much. Okay, molecular speed. So the Maxwell-Boltzmann distribution gives the distribution of molecular speeds. Let's say if you have different temperatures, T1, which is low temperature, then in this figure, which means the frequency of velocity of molecules against the velocity. So that means the frequency is very high for molecules which is at T1 temperature at this velocity. And then when the temperature is getting higher, then here, that's the most probable velocity. It has a very high frequency at this velocity. And when the temperature is even higher, then the most probable velocity is getting even higher. So what we see is when temperature is increasing, the curve flattens and the maximum shift to the higher speed. And the most probable speed for a given temperature is at the peak of the curve. For example, for this curve here, this is the most probable temperature, most probable speed. And here in pink, it's a fraction of molecules with speed from V1 to V2. Here it's the fraction of molecules with speed greater than VA. So this is a VMP. From the previous figure, we see the VMP is getting higher and higher. It's from, let's say, VMP1, which is according to the T1. Here is a VMP2, VMP3, according to T2 and T3 respectively. So when temperature is getting higher, the most probable velocity is getting higher. Okay, so the function of Fv, so here we have the curve. So this curve is described by a function here. The function of Fv is called Maxwell-Boltzmann distribution. It's shown here. It's complicated equation. Again, it doesn't show you how to derive this equation. So we're is the equation from? You just get this equation. Sometimes you might need it to do some calculations, but most of the time you just need to know there is an equation to describe the frequency of velocity at certain temperature for gas. Okay, so please read this equation and try to know each of the variables. Okay, last topic, the phase of matter. For an ideal gas, we ignore the interactions between molecules. However, for those interactions, actually they are important because those interactions are what makes matter condense into liquid and solid phase under some conditions. And each phase is stable in only certain ranges of temperature and pressure. So here, phase, we mean three different phases: solid, liquid, and gas. Gas. So the phase can be stable. For example, sometimes water is in solid phase, it's ice. It could be stable in a certain range of temperature and pressure. For example, in the pressure of atmospheric pressure, when the temperature is below 0 degrees, I mean centidegrees or degrees in Celsius, the phase of water is solid, it's ice. A transition from one phase to another requires phase equilibrium between two phases, and for a given pressure, this occurs at only one specific temperature. For example, when water is in a phase transition from ice to liquid water, you need a temperature which is 0 Celsius degree at the pressure to be atmospheric pressure. We can represent this condition on a graph with P and T. This is called phase diagram. We will show it in next slides. And each point on the diagram represent a pair of values of P and T. Okay, so here is the phase diagram. Let's say here you have some curves, and then these curves divide the entire PT space into three regions. Number one region, the light blue region, which is shown here. The light blue region, it's vapor or gas region. So in this kind of under this kind of condition, the material is in gas states. In the yellow condition here, the material is solid. And in this condition, the material is liquid. So for example, for water, this is the PA. Let's say for water, the atomic spherical is somewhere here. The temperature, the pressure, the atmospheric pressure is something here. So when the temperature is very high, you have gas phase of water, and when it's getting lower, you have liquid states or liquid phase of water. When the temperature is getting even lower, you will get solid phase of water, which is ice. However, if the pressure is not atmospheric pressure, instead, if it's something below the triple point, so let me erase the pen. So if the pressure, let's say, is here, it's very low, it's below the triple point, then under this kind of pressure, you will only have gas or solid. So if you try to lower the temperature, you will get the gas converted into ice or solid water directly without any liquid water. However, if your pressure is high enough, if your pressure, let's say, is here, then you will not have any, let's see, so the pressure actually is above the critical points. So if it's above critical point, the material probably changes smoothly with changing PRT rather than undergoing a phase change. So there's no phase change at all if T and P values are above the critical points. So that's PT phase. So atmospheric pressure on Earth is higher than the triple point, which is shown something here. So when the temperature varies, or depending on the temperature, water can be in vapor or liquid or solid. So for example, along this pressure here, you may have gas water, liquid water, and solid water. Okay, so this is a PVT surface in a more complicated case. If you have three variables. So here we have PT, and if you have one more dimension, which is V, then you have this 3D curves. It's a little bit more complicated. And if you project the curve into PT graph, you will get the same thing here. This is a PT, and here, this is PT. Okay, so that's the phase transition. This is the same thing in a 3D PTV form. Okay, so that's all the concept we have introduced in this chapter. So in this chapter, we have a lot of new concepts, and in most of the equations, you're not asked to derive the equations. You just need to know there is an equation. Sometimes when you need some calculations, you can refer to the slides or your textbook to see the equation and to do some calculations. So that's a requirement for the equations. For the concept, you just need to understand all the concepts introduced in this chapter. Okay, so this is chapter 18. I'll see you in next chapter.